So in chapter 3, actually, it still discuss about the Navier-Stokes equation and so on and so forth, but it's more on how to use Navier-Stokes equation in solving problems. Okay, so in chapter 1, okay, it is more around how to evaluate fluid properties. So we have the viscosity and so on and so forth. We have the gas, the ideal law, the gas ideal law, and so on and so forth. In chapter 2, we are focusing on derivation of velocity distribution. So now in chapter 3, we try to bring a few application, and then we try to with the Navier-Stokes equation. Okay. So, but before that, I would like to introduce you two major flow, which is the Couette flow, and another flow is the Poiseuille flow. So the Couette flow and the Poiseuille flow is actually the flow named after the scientist that proposed this idea. However, the flow of this type is actually, you already learned about this previously in your undergraduate might be or in your real application. So it's just a very simple flow. So, but the Couette flow is actually its official name. So it is okay for you not to know the Couette flow or the Poiseuille flow. So, but in our syllabus, I write as the Couette flow and the Poiseuille flow. Okay. So the difference is the Couette flow is it doesn't have any different in pressure. So we assume that in Couette flow, the pressure is remain atmospheric pressure for all the time. So that is the difference. Or the simple words about the Couette flow is actually the flow between two plates. Okay, that's what we learned in the first chapter in the viscosity about Newton law of viscosity, tau equal mu du dy. That's actually a part of the Couette flow. And the Poiseuille flow is actually the flow in pipe. So if I think you already know about, for example, you have a tank, and that tank connected with a pipe might be one or two. So and then this pipe will have water full inside that pipe, and then that pipe will create major loss, minor loss, and so on. So that is the Poiseuille flow, because when water flow in full, so mean you have a pipe and that pipe is fulfilled with water. So means that the velocity of fluid will determine the pressure. So mean the higher the velocity means the pressure will reduce. Okay, because that is the rule of thumb of Bernoulli equation. Okay, so we go for this one. Okay, we have the surface resistance with a uniform laminar flow. So, and we call it as a Couette flow. So in this section, we consider three two-dimensional laminar flows with parallel streamline. Okay, so parallel streamline, and the flows are steady and uniform. So I hope you could understand what is steady and uniform. And there is no change in velocity along a streamline. So this is the steady one. So using the momentum equation, we will first derive a general equation for the flow velocity and then apply it to the three specific problem. So first, we need to simplify our equation, and then we try to solve it according to these three situations. So it means that we have the flow produced by a moving plate, liquid flow down an inclined plane, and flow between two stationary parallel plates. Okay.
Excuse me, Doctor, please.
Yes?
These 3 points are a situation for a Couette flow?
Yes.
Okay. Doctor, please, can you give us a hint about a steady and uniform flow?
Okay.
Okay, thank you very much.
Okay, steady is actually when the velocity is actually constant, the layman term. Okay, the layman term is the velocity is not changing along the time. So means that the idea is the velocity is constant. So means that, for example, we have...
It means terminal velocity?
No. Terminal velocity means when an object, whether it is an object or a fluid, is falling down due to the gravity. when the gravity pull the object. So after certain time, it will reach the terminal velocity. But if the flow normally when you have a horizontal type of this one, so it is not pulling by the gravity, so it will not have any terminal velocity. So it is just a velocity. For example, flow in pipe. Okay, so here, okay, means that if the fluid flow like this one, so if you have 2 point, 1 point here and another point here, so you will find that the velocity at point number one is constant and means it's remain the same at point number two. Okay, means that the velocity is not changes along the streamline. So this is the streamline, for example. So if we check the velocity at here, and another point, the velocity is remain constant. So that is the steady. So however, you must know that if you have two streamline, for example, you have streamline here and here, so the velocity at this point and this point, okay, for example, here is 5 meter per second. So at this point is 4 meter per second. So means that the velocity is steady. Okay, because the idea of steady means the velocity is not change along the time with the time on the same streamline. So this is the same streamline, so the velocity is remain constant. So if the velocity from another streamline is changed, it's not considered as steady or not. Okay. I think you could Google it. It's very simple idea. So and then for the uniform here is you are check the condition of velocity is actually constant at the same location. So the main idea is steady here is about the changes of velocity about the time, and the uniform here is the changes of velocity about the location. So what is the location? So if you have a flow here, for example, a flow in pipe, the most simple one. So if you get the point number one here, so you will find that every velocity, every molecule here will have same velocity. So means this is the constant velocity for this location. So mean this velocity is uniform.
Doctor, this happened in the slip condition.
Yes, the slip condition. So this depend. For example, if you have a very large, I clear this one first. If you have a very large pipe, okay, so and then for sure in reality you have no slip condition, so mean the velocity will become like this. So there is start from the zero here, and then it has a velocity distribution, and then it will remain constant like this one. Okay. So means that might be the changes here is around 1 or 2% from the total velocity. So maybe you can assume that this flow is actually in uniform. So it's depend on you. So because might be the changes of velocity here will not affect all the calculation. So might be you could assume that this flow is actually uniform. So okay, so but if you have a small diameter of pipe like this, for example, and then the velocity distribution is something like this one, so might be you cannot assume that this flow is uniform because the velocity at this location and this location mean at the same cross-sectional location here is totally in the center, for example, is totally different. So here might be the velocity at all the location here, except at the beginning of this flow. It's not the same. It's almost all the velocity here is the same. Might be you could assume that this flow is actually a uniform. So in theoretical, actually the uniform flow here is used when you solve problem in ideal flow. So as we learned previously about the uh, linear source, sink, and vortex. So we assume there are no slip on that situation. So means that the flow is uniform. So it's depend on the situation. Okay. So
Doctor,
yes,
is there a relation between steady and uniform flow with the rotation and rotational flow?
yes, actually it has. So it because steady and uniform is actually two independent parameter. So it might be you have the rotational flow, steady and non-uniform or something like that.
Mm.
So okay, steady and
Okay.
uniform is actually independence. It can be happen at any flow condition, whether it is vortex or whatever. Okay, because we will have four conditions. One is steady and uniform, and also steady and non-uniform. And then another one is unsteady and uniform, and also unsteady with non-uniform. So we could have four situations.
Yes.
Okay. So means that it is good for you to just know about the steady and uniform. So because this is the very important assumption that need to be done first before you could solve problem. Okay, can we move?
Okay, doctor.
Okay.
Yes, doctor. Thank you very much.
So first, we need to derive a general equation before we could solve that three situation. So the idea is, for example, we have an inclined plate like this one, and then if we have a fluid flow from top to bottom like this, mean from your left to your right, so for sure the velocity will create the fluid will have velocity distribution like this one. So and then to analyze this one, so we just take a small portion of that flow. For example, we have this portion. Okay, so for example, we cut this one into a rectangular element. So and then we have this is an S direction, mean the inclined direction. So and then this is the Y direction, the Y axis. Okay, so and then okay, that is the axis that we have because it's relative to the flow of this fluid. So why this situation is taken? Because we assume that there are no pressure. So no pressure means the fluid will be flow in natural condition. So mean we need to incline this plate to make sure that water will flow with the gravitational effect. So and then when we cut a small element like this one, so we need to create a free body diagram. So I think you already know about this one. So the idea is first we must to write all the forces that act on that element. So for sure, when we have fluid flow, we have velocity, we will have pressure. So we assume that we have a pressure at this point, okay, P and delta Y, because we assume that the width here is unity. So mean that the width here is equal to 1 unit. Okay, so and then here, okay, we have another pressure. So might be pressure at this point. Pressure at this point is different with the pressure at the inlet point. So we write pressure at the outlet here at this surface as shown in the diagram. So it is P plus dPds delta S dy. So means that in another textbook, if you see another textbook, so it can be simplified as P plus delta P. So means might be delta P is minus or might be delta P is positive. So it depends, means there will be the changes of pressure. So times that dy times 1. So dy here is the height of this one and the width here is equal to 1. So mean the pressure time area will create force. Okay, that is the first assumption. And the second assumption is because molecule of fluid, okay, will give resistance according to the existence of shear stress. So there is a resistance from the shear stress. So we assume that the shear stress here will act at the reverse direction of the fluid flow. So if the fluid flow is in this direction, so we have here and here, okay, because it must be shear. So so we write tau times delta S. Okay, tau, you know, force is equal to tau times A, and A here is actually delta S times width, and width for this one is equal to 1. So because it is unity, so it will become tau and delta S. And again, at the top here, so we just write tau plus delta tau times ds, delta S. Okay, so to make it complete, it will become d tau over dy delta y. So because it is meaning of the changes of tau in terms of y axis. Okay. So that is the second force. And the third force is actually due to the gravity. So we know that gravity is pulling the liquid down like this one. And then because this plane is inclined at certain angle, so means we need to calculate, determine the component of that weight here. So and then I think you know that it can be resolved into two components. So and the component parallel with this plate is W sine theta. Okay, so this is the three forces that act on this control surface, on this element, control volume here. Okay, so and then the momentum is should be in equilibrium. So our free body diagram, so we assume that the total of forces is equal to 0. That means that we start to net the forces. So first about our pressure, so we have P delta Y minus with P dP ds delta Y, and we have this term. Okay, so and then we have the force due to the shear stress, so it will become this one. Okay, so and then we will have the net force of this one. So and then we have the gravitational force, and we know that the weight here is equal to mg. So and then it can be write as rho v and g, which is the v here is actually the volume. So I think the conversion is you already know about this. So you
Okay.
have, yes.
How do you get the net force due to the shear stress? The
Okay.
previous page. The shear stress net.
Okay. So we assume this is the positive one. So this is the in two different directions.
Okay.
Okay, so we just add these two forces, and one should be in negative sign because force is vector. So one is negative. So we take tau as is negative.
Okay.
Okay, so this is P is positive if you see the sign here. So and then here we have this one is positive because it's moved like this one because it is in parallel with this fluid motion.
Okay.
Okay. Okay. So and then for this one, I think you already know. So we have mass is equal rho time volume. So and then we could calculate the volume here. Okay, this volume is actually the volume of our element. So it is equal to delta S times delta Y and times width, which is equal to 1. So because the width is unity. Okay, so you have this idea. And then and then the idea of sine theta here. So the Couette proposed that it can be replaced with the minus dz ds. So it is referred to this sign. So we assume that the z-axis here, when it's falling down, downward there is the negative direction. So means that sine theta is now become negative dz ds. So we replace.
Doctor, excuse me. It looks like we apply the steps of Navier-Stokes question.
No, we simplified this first.
Okay.
Okay. So later on, I will show you about the Navier-Stokes. Please be patient, man.
Okay.
So if you keep asking, so people will lose the track. Okay.
Okay, I'm sorry.
Okay. Okay, let's go. We try to. I try to teach you in a very simple way to this one, because Navier-Stokes is sometimes it's very complicated. Okay, even researcher sometimes use the other simpler more simple method. Okay.
Okay.
Okay, so just we are talking about the forces act on that element. Okay, so and then the gravitational forces now can be described as this one. Okay, so mean we substitute the value of sine theta here. Okay, and so and then we replace with the minus and dz ds. Okay, so and then we sum all the forces. Okay, so I hope you could do this in at home. So we sum all the forces to 0 because we in equilibrium, so the forces is now in balance condition. So and then we divide by the delta S and delta Y. So finally we could get this one. Okay, so and then we replace, so we have rho and G later on. So we substitute the value of rho and G with mu, with gamma here, which means the specific weight. Okay, so and then here, for example, you have d ds times p plus rho g and z. So this is actually the rho and G here. So it's actually the constant. So means because we assume the most simple one is we evaluate this one is for liquid. So as you know, liquid is most of the liquid. I think there are no liquid can be compressed very hot, very much. So we assume that liquid is incompressible. So we remain the rho and G is not affected with the differential terms. Okay, so it means that rho G here is quite independent. So the dds here is actually focused on z only. Okay, so please try this at home. So you will find there is only dz over ds, and then we simplify this one into this term. Okay, this is the idea. So and then we have the shear stress here. So we have the shear stress here. So and then we know that shear stress is equal mu du dy. So and then we substitute the shear stress with mu du dy. So we substitute it here. So finally we could have this term. Okay, so it's become du dy here. Why? Because we have d over dy. And then we have mu another du dy here. So and then we bring the mu to the right hand side. Now we have d square u over dy square. So we have this term. So this term is actually this term and this term. This is the simplified version. So instead of we have rho g here, so we have gamma. So this is the basic equation for the Couette flow. So here, so we have du dy, d square u over dy square. So actually, if you doing from the Navier-Stokes equation, you must found that in nabla terms, so you will have d square u dy square. So finally, you will get this term equal to this one too. Okay, I will show you in the next one of these slide. Okay, so means that this is the simplified equation that we need to understand. We need to know before we could solve that three situation. So then, okay, please. So it is because an open book later on. Okay, for your test, it is only for chapter 1 and chapter 2 because in chapter 3 here, so we just start chapter 3 today. So I think it is not fair for you for to be included in test 1. Okay, so please study about chapter 1 and chapter 2 only. So and then, so we are going to solve that situation. So first we have flow produced by moving plate. So this is referred to the idea of viscosity actually. So for example, we have two plates. One is fixed. Okay, it can be both moving at a certain velocity. Okay, but normally it start with our general term, the representative diagram. So which is we have two plates. One is fixed and one is moving at certain velocity. So because we are this, okay, you could imagine that in this situation there are no walls between this one. So means that no wall is, we are not discussing about a rectangular hollow pipe, for example. Okay, so we are discussing about we have a two plate here. So and then between two plates, so we have a liquid. So because it is open to atmospheric pressure, so we assume that there are no pressure gradient. So this is the meaning of there are no pressure gradient in the direction. So I think you already know about this. So if it's open to the atmospheric pressure, so the pressure is almost equal to the atmospheric pressure. So means that we could neglect the existence of pressure at all. So we assume that dPds is equal to 0. So again, I hope you could understand the meaning of dPds means the S here is the distance of this one. So means that at any distance of S, there are no difference of pressure. So dPds is equal to 0. So and then there are also the streamline in the horizontal direction. So mean that dz ds is equal to 0. So we assume that, okay, might be this is the width and the molecule will flow straight like this one. So means that the changes along the dz here can be neglected. So if the changes occur, might be it is occur along the y-axis here and also to the x-axis here. Okay, so that's why to simplify the idea, so we have dz ds is equal to 0. Okay, so we have this one, and then we simplify into our first term here. So means that we have the d square u dy square here is equal all of this term. And then we found that dp ds is equal to 0 because our application now is open to atmospheric pressure, and at the same time dz over ds is equal to 0. So because we have this assumption, so now our d square u dy square is equal to 0. So I think from this stage, you know what to do. So we need to get the velocity distribution. So because we have the power of 2 here, the quadratic here, so we need to integrate 2 times. Okay, so we need to integrate 2 times. So Okay, so now I show you how to solve that problem by using the Navier-Stokes equation. So this is the Navier-Stokes equation, and you know that this is an x-axis, so we choose the Navier-Stokes equation for x direction. So, and you know that the motion of this one is a linear one, means using the Cartesian coordinates. So please take Navier-Stokes equation for Cartesian coordinate. So there are no rotational speed here, and the nature of the motion is actually in linear. So this is the Navier-Stokes equation in x direction. So we have the gravity at x here. So okay, later on, I hope you could simplify this one. So first, we assume that it is a steady flow. So a steady flow means that the velocity at the same streamline here means at point here, point here, point here, and so on is remain constant. So mean there are no changes of velocity along the time. So the dt here is equal to 0. So and then du dx is equal to 0 too. So why? Because du dx mean the changes of velocity along to the x-axis. It means that the velocity here and here is not different. So it means that du dx is equal to 0. So and then we assume that the flow is steady. So mean we just imagine that the molecule is moved from here in x direction only. So means that there are no molecule that's moving upward, moving downward, and so on and so forth. So we assume that there are no velocity of v and w. So and then again we have du dz is equal to 0 because of the width is, as explained previously. Okay. So and then the pressure is equal to 0. So and then again because du dx is equal to 0, so we don't have this term, and also we don't have this term. So finally we could simplify that d square u over dy square is equal to 0. Okay, so this is about the Navier-Stokes equation. If you want to use Navier-Stokes equation to solve this problem, it is okay. So it depends on you, because both equation will give you the same final answer of this one. Okay, so means this is the equation that we need to do. We need to solve to get the velocity distribution. Okay, so and then to solve that one, first, you know, because we have the quadratic terms of differential, so means we need to integrate them, integrate that terms twice. So we already know about this in previous lecture. So the most important parameter that you need to know is its boundary condition. So mean that we need to make two equations because we have two unknowns. Okay, so and then this boundary equation is actually reflect the situation that occur on its boundary. So as it named, so means that the boundary of this one is the molecule at this situation and also at this situation. So at this one we could write as at y equal to 0, the u is equal to 0, and at y equal L, so the u will become capital L. So if you see here, so because this is the y, so and then y equal to 0, the velocity is 0, and when the y is L, because it is mentioned as L here, so the velocity will will be equal to u. Okay, please be careful. Please do not remember this boundary condition, because this boundary condition actually depends on the situation. So might be it's in certain textbook they will give you 2h or 2x and so on and so forth, because the velocity at the center point here is the maximum one. So they are prefer to have 2h. So and then some textbook they will give you the coordinate for the center location is equal to 0, and you will have the positive h here and also the negative h here. So at this situation, you need to take y equal minus h and y equal to plus h, because your velocity distribution need to reflect the coordinates of your application here. So here we have the y0 and y equal to L. Then we have the boundary condition of this one. So I simplified the integral process. So in previous note, we have that one. So if you integrate this equation twice, you will get u equals C1y plus C2. So and then if you substitute the velocity at the boundary condition here into this equation, so you will find that u is equal u times y over L. So this is the velocity distribution of that situation. Okay, so and then we have shear stress equation, so which is tau is equal mu du dy. So here, this equation is still not valid to calculation because we have in term of differential, we have du dy. So we need to solve this term first. So to solve this one, we know that u is equal capital U y over L, and if we du dy this term, we will get u over L. That's why we could substitute this one, tau is equal with mu du dy. So this idea is actually proposed by Couette, a French scientist. So until now, we call this kind of a solution is a Couette flow. Okay, so this is the simple example. So for example, we have the fluid of between plates SAE 30. So at 38 degrees Celsius, the plates are spaced 0.3 millimeters apart, and the upper plate is moved at velocity of 1 meter per second. So what is the surface resistance for 1 meter square of the upper plate? So we calculate the shear stress according to this equation. So we substitute with the value. So we have the U is 1 and L is the gap here. So the L here is actually reflect with our diagram here. So it's actually the difference, the distance of these two plates. So and then we substitute the value. So we get it is 333 Newton meter square. So if the area is 1 meter square, so we get the force occur according to the shear stress of that oil is 333 newtons.